Okay, so now we're going to think about where a chemist's criteria for spontaneous change comes from. So we're going to basically concentrate on being able to measure properties of the system in order to determine delta S total. So up to this point, we've said if you want to know if a process is spontaneous, the total entropy in the universe has to change in a positive way for a spontaneous process. If the delta S total of the universe equals 0, then the process is in equilibrium. And if it's less than 0, the process is non-spontaneous, or you could say you have to put work in to make the process happen, or you could say it's spontaneous in the opposite direction. So those are our criteria from the second law, and those are the only criteria there are. So we define functions as chemists that are useful because they allow us to measure a change in total entropy of the universe just focused on what happened to the system. So we're going to talk about Helmholtz energy and Gibbs energy. Helmholtz is less familiar to you because it's going to be valuable when you carry out a process at constant temperature and volume, and chemists rarely do that. We did that in the Baum calorimeter in 266, but other than that, it's really quite rare to have a constant volume reaction. So for a constant volume process, we're going to define Helmholtz energy, A, to be equal to internal energy minus Ts. And so if I write that then as a differential, a change in Helmholtz energy would be equal to a change in internal energy minus, and I'll just expand this, we can change entropy and we can change temperature, holding the opposite one constant to get the overall change in T times S. So at constant T and V, then this term will be 0. So that will go away, and dq or du equals dq at constant V. So this is the important part of holding volume constant. Getting rid of this term is the important part of holding temperature constant. So now I have change in Helmholtz energy is equal to dq for a constant volume process minus T ds. If I divide both sides by T, I get change in Helmholtz divided by T equals dq over T minus ds, because it was TDS. So if I divide that by T, it's just ds. And we know that the total entropy change of the universe is equal to the entropy change of the system plus the entropy change of the surroundings. And it's true that the heat that flows in or out of the system just goes in the opposite direction to the surroundings. So dq for the system is equal to negative dq for the surroundings. So dq over T equals negative of the change in entropy of the surroundings. So I can take this term and replace it with minus ds of the surroundings. So now I have dA over T equals negative change in entropy of the surroundings minus change in entropy of the system. If I multiply each side by -1, I get negative dA over T equals ds surroundings plus ds, and we know that is total change in entropy of the universe. Therefore, because of this, so we know that ds total has to be greater than 0 for it to be spontaneous. And dA over T, the negative of that, is going to be equal to the positive of ds. So if ds total is negative, or df total is positive, then dA is going to be negative. And so the criteria will just have the opposite sign, essentially, because dividing by T can't change the sign. So remember, each of these, when I look at these free energy functions, they're always going to be restrictions. So it's only true that a dA change is less than 0 is spontaneous. It's only true if that process was carried out at constant volume and temperature, because that's the only time du equals dq, and that's the only time we don't have that temperature change anymore. So the second function that we define for a more common situation is Gibbs free energy. So Gibbs energy, which is the one that you've grown accustomed to using. So by definition, it's enthalpy minus TS. So an infinitesimal change is equal to DH minus TDS minus SDT. Now, if we put the restriction that we're at constant temperature, that third term goes away and DG equals DH minus TDS. At constant pressure, DH equals DQP. So it equals the heat transferred at constant pressure. So I can put that in there, and I guess I'll remind us that that's only 2 at a constant pressure. So now that says that DG, if we carry out the process at a constant temperature and pressure, is equal to DQ minus TDS. So we go through the same derivation. DS total is equal to minus DQ over T plus DS. And so if I multiply both sides by T, I get minus TDS total is equal to DQ minus, because the negative got rid of that and changed that positive to negative. And therefore, what you will see is that these two are the same. Therefore, a change in Gibbs free energy if the process is carried out at a constant temperature and pressure is equal to negative TDS total. Therefore, if DG at constant temperature and pressure is less than 0, it's spontaneous, because it was spontaneous if this was greater than 0. And T can't change the sign, so negative of a positive number gives you a negative. So our criteria, our use of a Gibbs free energy change as a way to determine if something's spontaneous is really just using the second law. And you want to make really careful, you want to think really carefully to make sure that you never use a Gibbs free energy change if the process isn't at constant temperature and pressure to decide if something's spontaneous. What are some other uses for these two functions? They actually have other valuable properties. So if we look at dA, so if we look at Helmholtz free energy, it will be equal to du minus TDS minus SDT. du is equal to dq plus dw. If we pick a reversible path, and this is kind of subtle, but you can pick any path you want because A is a state function. So if both of these are reversible, I'll get the same change as I would if both of these were irreversible. So if I pick a reversible path, then dq equals TDS. So dq reversible equals TDS. So I can replace dq with TDS. I still have my work, but now this TDS and TDS can cancel. And if I'm at constant temperature, this will cancel. And therefore, a change in Helmholtz free energy for a constant temperature process is equal to the maximum amount of work the system can do, whether it's expansion work or other work. It's the maximum because, remember, if I pick a reversible path, then I have the maximum work. And in order to cancel the TDS, I had to pick a reversible path. So the maximum, because it was a reversible path. So if you can measure the change in Helmholtz free energy at constant temperature, you know the maximum amount of work you could get out of a system. The Gibbs energy also tells you about work, but we'll see just slightly different. So Gibbs energy equals enthalpy minus TS. So it equals DH minus TDS minus SDT. If I replace DH with DU plus PDV plus VDP, because H equals U plus PV, then I replace DU with DQ plus DW. So we'd get DG equals DQ plus DW plus PDV plus VDP minus TDS minus SDT. And let's see how that simplifies. So If I pick a reversible process, then dq equals TdS, so I can replace that dq. And work should be equal to the expansion work. If it's reversible, this is the pressure of the gas and not external pressure, so it's negative PdV plus any additional work. So it might be electrical, might be surface tension, any work other than expansion work. So if I replace dq with TdS and I replace dW with expansion work plus the additional work, then we will see that lots of stuff cancels. TdS, TdS, PDV, PDV, those cancel. And then if I set the restriction of constant pressure and temperature, this term cancels and this term cancels. And all we're left with is this term and its maximum once again, because we picked a reversible process or a reversible path. So the Helmholtz free energy and the Gibbs free energy can be used to decide if a process is spontaneous. The Helmholtz free energy change if the process is carried out at constant volume and temperature. If the value is less than 0, it's spontaneous. If a Gibbs free energy is carried, if the process is carried out at constant pressure and temperature, then a negative change in Gibbs free energy will tell us the process is spontaneous. You can also use a change in Helmholtz free energy to determine the maximum work if it's a constant temperature process. You can get the maximum additional work from a change in Gibbs free energy if the process is carried out both at constant pressure and constant temperature. So we are going to skip the Born equation. That won't be useful for our journey to understanding equilibrium. So I think I'll go ahead and do this last section in the same video. You can always stop it if you want to break. So now we're going to combine the first and second law, and we're going to see some pretty cool stuff in the process that calculus will reveal to us. So the first law says that du equals dq plus dw. And if there's no additional work and we pick a reversible path, then dq equals TdS and dW equals negative PDV. Therefore, this fundamental equation is combining the second law with the first law. So we have both entropy and internal energy as a function of each other. And what this tells us as we look at calculus is that you could define internal energy to be a function of entropy and volume, because this equation is showing you how internal energy changes when entropy and volume change. So if we set internal energy and pick the two variables to be volume and entropy, then we could write the total differential from calculus. And the total differential would be entropy or internal energy changes if entropy changes and if volume changes. And the proportionality constants are these partial derivatives. But now if we compare this back to the fundamental equation, it tells us that this derivative, the change in internal energy with respect to entropy holding volume constant, has to be equal to temperature, because that's the coefficient out front ds in each of these. So that's something you could never figure out without just looking at the calculus. Same is true here, that the internal energy changes with respect to volume holding entropy constant has to be equal to negative P when you compare those two equations. So we've learned something about these partial derivatives that would have been impossible to learn if we hadn't thought about comparing the calculus to the physics. So there's a typo in the toolkit, but if this is just out of the toolkit and they have a Y here at the end, you'll notice it if you go through it. But the important thing about the exact differential, I introduced this when we talked about this in the last focus, is that if f is a state function, then you can change it in any way you want. You can take any path to change the function f. So we're going to talk about that in reference to all of our thermodynamic functions. So when we write its total differential, we notice that each of these partials is some function of x and y in general. And because it's an exact differential, then take the first derivative with respect to x, holding y constant, and then take the derivative with respect to y, holding x constant. That has to be equal to doing it in the opposite order. Change this function with respect to y, holding x constant, and then change x, holding y constant. So those two have to be equal to each other if it's an exact differential, because that's equivalent to saying that it doesn't matter which path I take. I can change x first, I can change y first, but in the end, if I change them both in the same way, I end up at the same place. And so from that, if we look back at this, something you could never have figured out without that calculus of an exact differential. So this is the first derivative, t. So now if I take the derivative of this with respect to the opposite variable, with respect to v, dt dv constant s has to be equal to the derivative of this with respect to s, holding v constant. So that is one of the Maxwell relations, and that is just absolutely amazing. So we'll see that you could never have figured out there was a relationship between these two changes unless you had looked at this calculus to recognize that you had to have an exact differential. So when we're together in class, we'll derive some other Maxwell relations. That this one started with the total differential for internal energy changing. We're going to look at the other three that come from starting with a dH, a dG, and a dA, but we'll get some really interesting relationships that will help us understand relationships between physical properties that we never could have known if we didn't have this understanding of calculus. Okay, so let's now think about how Gibbs free energy changes with pressure and temperature. So Gibbs free energy is H minus Ts. So if we look at a change in Gibbs free energy, it'll be a change in H minus a change in Ts. We can expand the change in Ts to be two terms, changing S and T separately. Enthalpy is U plus PV. So dG is du plus PdV plus VdP. So just expanding this to be dH, and then our TdS and SdT. dG then, if we put all of that in, so then we put in for du. du is T ds minus P dV. So if we put all of that in and cancel everything that cancels, we end up knowing that Gibbs free energy changes as a function of pressure and temperature. And this is called the fundamental equation of chemical thermodynamics. So the partial derivative are the proportionality constant between a pressure change and a Gibbs free energy change is volume. Between a temperature change and a Gibbs free energy change is negative S. So when we look at this, that means that Gibbs free energy changing with pressure holding temperature constant, so out front of the dP, has to be equal to V. So this partial has to be equal to V, and this partial has to be equal to S. So Gibbs free energy changes as a function of pressure holding temperature constant, and it changes as a function of V. Gibbs free energy changes when temperature changes, holding pressure constant as a function of what your entropy is, and that's a negative out front. So we can look at those, and it's always important to think about what those tell you, what physics you can understand from looking at the math. So entropy is always greater than 0 for a substance. So G always decreases when temperature goes up. So Gibbs free energy, T goes up, is a function of negative S, and S is always a positive number. So G always decreases when the temperature goes up. dg dt constant p, so that partial derivative, how does Gibbs free energy change with temperature holding pressure for constant, becomes more negative as S increases. So the greater the entropy, the greater the slope, essentially, of the line that relates Gibbs free energy to temperature. So Gibbs free energy decreases more sharply when increasing temperature when S is large. So that would mean for a gas, you would have a greater change in entropy with temperature than you would for a liquid, which has lower entropy. Volume is always greater than 0. Therefore, G always increases when the pressure is increased. So this will tell us there's a positive relationship. And because change in Gibbs free energy with a change in pressure increases with volume, Gibbs free energy is more sensitive to pressure when the volume is large. So that's also thinking about gases are going to have greater changes in Gibbs free energy with pressure because their volume is so much larger than liquids and solids. So we will derive these on the board. So each of you will get the privilege of putting one of these on the board. So how do we go from these partial derivatives being equal to volume and negative S to the equations that they give you on the board, which relate how Gibbs free energy changes with temperature to a delta H, how Gibbs free energy changes with pressure if you have a compressible substance, and how Gibbs free energy changes with pressure if you have a perfect gas. So each of you will put one of those on the board when we're together so that we understand where they come from. This one, we're going to use a whole bunch, and we'll use this one somewhat. So there'll be equations that are super important. This will be absolutely essential when we derive the expression for an equilibrium constant. So that is focus 3.